Equilibrium between atoms of different masses. Consider a collision between two different atoms having masses m1 and m2. Denote the velocities of these atoms before the collision by v1 and v2 respectively. Denote their velocities after the collision v1 prime and v2 prime respectively. It is of interest to investigate the energy transferred from one atom to the other as a result of the collision. Introduce the relative velocity v1 minus v2, capital V, and the center of mass velocity m1 v1 plus m2 v2 over m1 plus m2, which is c. The relative velocity after the collision is then v prime, v1 prime minus v2 prime. In a collision, c remains unchanged by virtue of conservation of momentum, while the magnitude of the relative velocities should be the same by virtue of conservation of energy. Show that the energy gain delta epsilon 1 of atom 1 in a collision is given by 1 over m1 v1 prime squared minus v1 squared is m1 m2 and 1 plus m2 to the power minus 1, center of mass velocity dot product with the difference in the relative velocities after and before the collision. So basically the problem is asking us to transform from v1 prime and v1 to c v prime and v for relative velocities. Okay. So the first thing I would like to do is to verify some of the statements about the physics of the problem. So let's start with noting what we have here. The relative velocity of m1 with respect to m2, or the particle with mass m1 and or the atom with mass m1 with respect to the atom with mass m2 is given by capital V vector, which is v1 minus v2. So this is before the collision. Before the collision. Let's call this equation 1. The center of mass velocity in the lab frame. The center of mass velocity in the lab frame is C is equal to m1 v1 plus m2 v2 divided by m1 plus m2, and this must be equal to m1 v1 prime plus m2 v2 prime divided by m1 plus m2. This is conservation of momentum. So let's elaborate on this a little bit. I'm going to call this equation number 2. This comes from the fact that the center of mass location is m1 r1, the position vector of the first atom, m2 r2, position vector of the second atom, divided by m1 plus m2. Therefore, the center of mass velocity is c, which is dr center of mass dt. So if you take a time derivative, you get m1 dr1 dt, which is v1, plus m2 dr2 dt, which is v2. So that is divided by m1 plus m2. So v1 is dr1 dt, v2 is dr2 dt, the change in the position vector per unit time. The initial momentum of the system is m1 v1 plus m2 v2, which must be equal to the final momentum of the system, m1 v1 prime plus m2 v2 prime. Why should the momentum be conserved? The net external force acting on the system is 0. So we have the change in momentum dp dt equals to 0. So that implies that the change in the momentum must be 0. So conservation of momentum applies, as suggested by the problem. Now let's continue. The relative velocity of m1 with respect to m2, the atom with mass m1 with respect to the atom with mass m2, is capital V prime, which is v1 prime minus v2 prime after the collision. After the collision. So let's call this equation number 3. And we have talked about conservation of momentum. So we have seen that C remains unchanged by conservation of momentum. In the collision process. At the same time, also we see that kinetic energy must be conserved, because we're assuming elastic collision. So the kinetic energy was initially 1 over 2 m1 v1 squared plus 1 over 2 m2 v2 squared. This must be 1 over 2 m1 v1 prime squared plus 1 over 2 m2 v2 prime squared. So we see that the 1 over 2's will disappear, and this equation can be written as m1 v1 squared minus v1 prime squared is equal to m2 v2 prime squared minus v2 squared. So this we can expand as m1 v1 minus v1 prime dot product with v1 plus v1 prime, and this is equal to m2 v2 prime minus v2 dot product with v2 prime plus v2. So since we also have conservation of momentum, so this coupled with the conservation of momentum, delta P is equal to 0 implies m1 v1 plus m2 v2 is equal to m1 v1 prime after the collision plus m2 v2 prime after the collision. So this implies we have m1 v1 minus v1 prime is equal to m2 v2 prime minus v2. So going back to our equation that we obtained from the conservation of kinetic energy, we see that m1 v1 minus v1 prime dot product with v1 plus v1 prime must be equal to m2 v2 prime minus v2 dot product with v2 prime plus v2. But since we have m1 v1 minus v1 prime is equal to m2 v2 prime minus v2, these two will cancel, so that we will have v1 plus v1 prime is equal to v2 plus v2 prime. So this means that if you write v1 minus v2 on the left hand side, this must be equal to v2 prime minus v1 prime on the right hand side, while v1 minus v2 is basically what we called capital V, relative velocity of m1 with respect to m2. So this is capital V. This must be equal to minus v1 prime minus v2 prime, which is capital V prime. Therefore, the magnitude of the relative velocity must be the same as suggested by the problem statement. Okay, so we will continue with our calculation from equation 2. From equation 2, we have so let's go back to equation 2. That's the statement of conservation of momentum. m1 plus m2 times the center of mass velocity is equal to m1 v1 prime plus m2 v2 prime. So we can write v2 prime as m1 plus m2 m1 plus m2 divided by m2 times the center of mass velocity c minus m1 over m2 multiplied with v1 prime. So let's call this equation so v equals v prime magnitudes, we call this 4, and let's call this equation number 5. Alright, so from this equation and going back to the definition of the relative velocity after the collision, equation number 3, So from 3 and equation number 5, we have for v1 prime, capital V prime, which is the relative velocity, plus v2 prime, which is capital V prime, plus for v2 prime I substitute the answer from equation 5, m1 plus m2 divided by m2 times the center of mass velocity minus m1 divided by m2 v1 prime. So if I rearrange this for v1 prime, collecting v1 prime on the left hand side, I see that 1 plus m1 over m2 v1 prime must be equal to the relative velocity after the collision plus m1 plus m2 divided by m2 times the center of mass velocity c. Therefore, we can obtain for v1 prime the following result. v1 prime is m2 divided by m1 plus m2 multiplied by capital V prime, relative velocity after the collision, plus m1 plus m2 divided by m2 times the center of mass velocity. So we have achieved our task. We have gone from v1 prime to the relative velocity after the collision and center of mass velocity c. So if I do the same exercise for v1, then I will be able to write the change in its kinetic energy in terms of c and the relative velocities. So similarly, I continue the same exercise from equation number 2. Let's go back to equation number 2. That's conservation of momentum. We can write m1 plus m2 times c is m1 v1 plus m2 v2, so that we can obtain for v2 m1 plus m2 divided by m2 c minus m1 divided by m2 v1. So this equation I'm going to call number 7, and from equation 1 and 7, from 1 and equation number 7, we can write equation number 1 is the definition of relative velocity before the collision. For v1 we have capital V plus v2, and for v2 I substitute the result in equation number 7, m1 plus m2 over m2 times c minus m1 over m2 times v1. So if I collect v1 on the left hand side, I obtain 1 plus m1 over m2 times v1 is equal to the relative velocity v plus m1 plus m2 divided by m2 times the center of mass velocity c, which gives me for velocity v1 before the collision m2 divided by m1 plus m2 multiplied by the relative velocity v plus m1 plus m2 divided by m2 times the center of mass velocity c. That's equation number 8. So basically I have completed the transformation from v1 and v1 prime to capital capital V prime and the center of mass velocity. So we can write equation number 6 and equation number 8 as the following. So the end result of our transformation v1 prime, so basically distribute m2 over m1 plus m2 into the equation, we obtain for v1 prime m2 divided by m1 plus m2 v prime plus the center of mass velocity c, and for v1 we can write m2 over m1 plus m2 relative velocity v plus center of mass velocity c. So therefore I can calculate the change in the kinetic energy of the first atom, which is 1 over 2 m v1 prime squared minus v1 squared. So if we substitute this result into this equation, for the change in the kinetic energy I can write as 1 over 2 m1. For v1 prime squared I have m2 over m1 plus m2 squared v prime squared plus c squared plus the cross term 2 m2 over m1 plus m2 dot product of v prime with c, and then subtract from this v1 squared, which is m2 squared over m2 divided by m1 plus m2 parentheses squared v squared, and then I will have minus c squared, and then I will have minus 2 m2 m1 plus m2 dot product of v with c. Now here you will see that m2 divided by m1 plus m2 squared v prime squared is going to disappear with the term that has v squared, because we have v prime magnitude is equal to magnitude v. That was equation number 4 that we have obtained. Okay, so this is equation number 4 that we have obtained, so we're substituting that here. Therefore we can write the change in the kinetic energy delta epsilon 1 as 1 over 2 m1. Now we have 2 m2 m1 plus m2. So we have the dot product of c with v prime minus v. So we see that we can write this equation as the change in kinetic energy of the first atom is 1 over 2 m1 v1 prime squared minus v1 squared. This can be written as, since the 2's cancel here, m1 m2 m1 plus m2 to the power minus 1, the dot product of the center of mass velocity with the difference in the relative velocities after and before the collision as suggested by the problem. Okay, so we have introduced a transformation of velocities. The relative velocity of m1 before the collision is v1 minus v2, so that's with respect to m2, so that's the first one. And the second one is equation number 3, that's after the collision, the relative velocity after the collision. We have shown that using conservation of momentum, the center of mass velocity should be the same before and after the collisions, and we have the conservation of momentum since there is no external force here. The kinetic energy is conserved. This is an elastic collision that we're considering, and we have basically made a transformation of the velocities v1 and v1 prime to center of mass velocity c and the relative velocities v and v prime using these equations. And finally, we have obtained the result suggested